Welcome to the Problemers Channel Season 3, Episode 35, the episode which I titled Twice Telescopic Rotating Antenna, because in this episode we will explore the kinematics of such a device. But before we deep dive into the underlying differential geometry of that problem, as a traditional and friendly reminder, if you're joining our channel mid-season, then first of all, thank you very much for your vote of confidence. Thank you for subscribing to our channel and welcome to our channel. And second of all, perhaps the most efficient way for you to gain the most academic benefit from the material that we present on this channel is for you to go to the homepage of our channel, and at the top of that page in the channel's trailer section find the episode titled The Problemers Channel How To. We recommend that you watch that episode in its entirety, follow all the instructions that we give in that episode, because in that episode we explain and motivate everything that we do on this channel. If you have questions, by all means do ask. The best way to ask your question is to find an episode on this channel that is of interest to you and use the comments section under that episode, and I will take it from there. And of course, and as usual, I would like to extend my deepest gratitude to all the current subscribers and the current supporters of our channel. In the physics problem S3P8, we are asked to recover the law of motion and the surface over which a point associated with a twice telescopic rotating antenna executes the motion in the following manner. Our twice telescopic antenna consists of two mutually orthogonal arms, the logically vertical arm and the logically horizontal arm. And the telescoping process of this arm unfolds as follows. The vertical arm of our antenna moves or telescopes out along the proverbial z-axis in the upward direction perpendicularly to the ground level, let's say. And as that telescopic motion is taking place, the horizontal arm of that antenna is also telescoping out and away from the vertical arm of our antenna, and that telescoping of both arms in mutually perpendicular directions unfolds as follows. The change in the length of the vertical arm of the telescoping antenna is a constant multiple of the change of the length of the horizontal antenna, or vice versa. It doesn't really matter. What that means is that, let's say, if with h we designate the length, the current length or the current height of the vertical arm of the antenna, then h1 relates to d1, and d1 is the distance of the outer edge of the horizontal telescoping out antenna at the moment of time 1 will be the same as h2 divided by d2 as h3 divided by d3, and so on at any moment of time k. hk over dk is a constant real number. What that means is that the ratio of the sides of the right triangles at any point, which we can obtain by taking snapshots of our twice telescopic antenna at this point, is one and the same, and in the sense that this particular constant defines the tangent or the cotangent of this here angle. Let's say we designate this angle as lambda 0, so if we take it as h divided by, at any time, hk divided by dk, this will be the cotangent of the angle lambda O, and if we take it the other way, dk, in other words, the length of the opposite side divided by the length of the adjacent side, dk over hk, this will define the tangent, the trigonometric function of tangent of that angle lambda 0. And on top of everything else, as this compound motion is taking place, is unfolding, the whole thing. Both arms rotate in the horizontal plane with the constant angular velocity of omega 0. And of interest to us is the life story, the kinematic life story of the point M. Let's say we'll designate it M for moving point. And we're also told that either way, we can throw all sorts of parameters at this problem. We can lock in the ratio of the height of the vertical antenna to the length of the horizontal antenna. It doesn't really matter. Perhaps in order to make this problem have the smallest number of parameters, we can introduce this angle right away. And we're also told that this point that sits on the far side of the horizontal telescoping out arm of our contraption is moving away from the base of the antenna, which we can designate with the letter O, with a velocity that is linearly proportional to the distance of that point from the origin. And under these conditions, we're asked to recover the low motion of the point M. And ideally, we also want to figure out over which type of surface does this point execute its motion. The truth of the matter is that in college, pretty much no one will give you the romantic version of such a problem as I give you, and instead you will be given the so-called hardcore or raw problem in its pure academic fashion, and it is your job, should you choose to accept it, is to come up with a romantic version or with a version of the official raw academic problem that casts a sort of mechanical light on that raw and pure academic problem. And in my view, any time that you spend on coming up with a romantic version of the given problem is a time well spent, because it will help you understand and decompose the usually compound and sometimes quite complicated motion of a given point into simpler components, into simpler parts and pieces, and this will help you wrap your brain around the problem and hopefully solve this problem. As such, if you take my romantic version of the problem statement that I gave you a few seconds ago and lay it on top of the raw and pure academic setting, then you will obtain the following. Imagine that we have in a given, let's say, traditional orthogonal Cartesian coordinate system embedded into a typical Euclidean 3D space. The origin marked with O, and through that origin there passes a straight line OL, shown in yellow, in such a way that it forms a non-trivial angle lambda 0 with the vertical axis OZ. And that straight line is rotating or tracing the surface of the right circular cone, which I designated with the lower kc, and that sweeping motion of the straight line L over the surface of the right circular cone means that the corresponding axial cross-section portrayed with the right triangle OZL and cross-hatched in yellow color, as is shown over here, is rotating around the z-axis with a constant angular velocity omega 0. We can even show it as a vector. And as that motion of the axial cross-section OZL is taking place, uniform circular motion, along the straight line OL, there moves a point M, shown in blue, let's say away from origin, and we're told that the velocity of that point, the velocity of the point M, is proportional. In the previous segment I used the letter K, but let's say I will use the letter M, it doesn't really matter, proportional to the distance of that point from the origin. And under these conditions, we are asked to recover the low motion of the point M, and it is evident right away that the point M traces the surface of a right circular cone. Now, my idea of coming up with a romantic version of such pure academic problems is again to help us understand what is going on in this problem. And in this problem now, you should be able to see that the point M participates in 3 independent motions. And what are these motions? Well, first of all, at any point on time, of course, if we project the point M orthogonally onto the z-axis, like so, we will obtain another right triangle. And this is how you see my, for example, genesis of my idea of how we have the telescopic antenna whose vertical arm grows or telescopes upward along the z-axis, then the perpendicular arm that is orthogonal to the vertical arm telescopes out. As the point M moves over here, there will be another right triangle, and before that there was another right triangle. So if we take a bunch of snapshots of our point as it executes its motion over the surface of a right circular cone, this is exactly what will happen. So the 3 independent motions in which the point M participates are the following. You should be able to understand this. The motion of the point along the z-axis upward, and the motion of the point M in the x or y plane, essentially x or y plane, because at any point, if we cut our right circular cylinder with the plane that is orthogonal to the z-axis, this is precisely what we will have. We will have a plane that is parallel to the x or y plane, and in that plane, the point M will be moving away from the version of the origin of the x or y plane, moving away, and it will be rotating in that plane at the same time. So 3 independent motions are 2 translational motions and 1 rotational motion. And if we project the point L, which we simply use to designate our generating straight line L in a sense, and don't forget that in terms of the right circular cone, that straight line OL will be called a generatrix. If we project that point L orthogonally onto the underlying plane X or Y, we will obtain the point P, so that the line segment LP, let's write it down, LP, will be orthogonal to the plane X or Y at any time. And then the line segment OP will be parallel to the line segment ZL. This is what I captured over here. ZL is parallel to OP. Not only that, but because the projection is orthogonal, and in some sense the point Z is what? Again, is the image of the point L under the orthogonal projection of the point L onto the Z-axis. Both projections are orthogonal, and not only these straight line segments are parallel, they have equal length. The distance ZL is equal to the distance OP. And in this particular case, we can say, how can we translate into mathematics the physical interpretation of the fact that the axial cross-section OZL rotates about the axis Z with a constant angular velocity? Well, that means that at any point in time, if we construct a plane XOZ, this plane right here, this plane, and the plane precisely ZLO, this plane, then these planes will form a dihedral angle. And to that angle we will refer as the longitude of the point M. So in other words, we will use the polar coordinate system in space, and in that polar coordinate system in space, we will capture the position of the point M with this dihedral angle, and to that dihedral angle we will refer as the longitude of the point M. And because the point L projected orthogonally onto the plane X or Y produces the point P, if we connect the point O with the point P, this dihedral angle will be formed by the, let's say, fixed plane XOZ and the rotating plane ZLO, or in this case ZLPO. This plane will be rotating about the z-axis with a constant angular velocity. That means that at any point of time, the straight line OP will be also doing what? It will be rotating in the X or Y plane with the constant angular velocity omega 0, exactly the same angular velocity because a plane intersects with another plane over a straight line, and that straight line belongs to the plane ZLPO that rotates about the z-axis with a constant angular velocity. That means that the straight line OP that belongs to the rotating plane also rotates with that plane with the same angular velocity. So there we have it. The straight line OP rotates in the plane XOY with the same constant angular velocity. Moreover, the projection of the point M in the orthogonal fashion onto the underlying XOY plane will fall where? That point M with the subindex XY, to reflect the fact that the projection of the point M is taking onto the plane XOY, will be falling exactly where? It will be falling exactly on the straight line OP. So in this particular case, if we ignore the situation that unfolds along the z-axis, remember the translational motion of the point M over the z-axis, then in the plane X or Y, or in some sense in any plane that is orthogonal to the z-axis and cuts our cone, this will be the characteristic representation, or it will be representative motion of our point M, the motion that unfolds in the X or Y plane. And what will happen over here? Well, we will come back to this in a second, but over here, look at this. We will have a straight line, OP, rotating in the X or Y plane with the constant angular velocity. And then we will have also a point MXY moving away from the origin at certain velocity. So the question over here right away, what do you think is the trajectory of the point MXY in the plane XOY? Think about it. I'll answer this question in a minute, but fundamentally, this is the official or raw and pure academic problem. And in such a problem, we will also track the position of the point M with its radius vector OM, the radius vector OM. As I explained before, the longitude phi will be a dihedral angle between the planes X, O, Z, the fixed plane, and the rotating plane Z, L, P, O. And we will also introduce the so-called latitude, which we will designate with the letter psi 0. We now understand that as our point executes its motion, as I explained earlier, its position in space can be completely described with the following three numbers. The dihedral angle, to which we will refer as the latitude of the point M, phi, the radius vector OM, the dihedral angle theta, and the angle between the moving straight line OP and the moving straight line OL, to which we will refer as latitude, and we will refer to this latitude as the letter psi 0. And under these conditions, we want to capture the law of motion, or a parametric equations, a set of parametric equations that describes the evolution, the time evolution of the point M as it executes its motion. Now, the most straightforward thing to do over here is to realize the following. Because the straight line OL traces or sweeps the surface of a right circular cylinder C at all times, and the point M is sitting on that straight line. What does that mean? That means that the angular displacement of the point M with respect to the straight line Z is always one and the same. And we will refer to that angle between any, as a matter of fact, any generatrix of a right circular cone C as lambda 0. And what does that mean? Well, again, remember that the vertical straight line, or the axis Z, is perpendicular to the X or Y plane. And that means that at any time, as I explained earlier, the point P that moves in a certain way in the X or Y plane participates in the formation of the straight line OP that moves around, and the angle between the moving straight line OP and the moving straight line OL is actually what? It is, how do we compute the magnitude of that angle? Well, psi 0 will be equal to what it will be equal to pi over 2, the right angle, minus our angle lambda 0. And that angle, because the angle lambda 0 remains the same, in other words, if we cut our right circular cone, the right circular cone with the plane that passes through the axis OZ, then we will obtain what? We will obtain a triangle that will look like this. The sides of this triangle will be the same. What do we call this triangle? This triangle will be isosceles. And then in this triangle we'll construct the height. So this angle right here is precisely lambda 0. It is very straightforward to see it in your mind's eye. And then over here, this will be the representation of the x or y plane viewed from the side. This is our latitude psi 0, you see. So what is the magnitude of the angle psi 0? Well, it's pi over 2 minus lambda 0. This is what we have. This is the equation number 1, and this is already one equation on the books. Let's put it into a nice little box, and we have it. Next, let's look at the dihedral angle phi, to which we refer as the longitude of the point M as it runs over right circular cone. So what can we say about this angle? Well, it's also very straightforward. The magnitude of this angle by the problem statement can be captured as follows: omega 0 times t. So this is how the magnitude of the longitude of the point M that moves around the outer surface of a right circular cone changes over time. This is our second parametric equation. You see, this problem is not as difficult as it sounds, and it's probably, once you set all the things up, choose the proper coordinate system, then the solution of this problem is actually much shorter than everything that surrounds it and sets it up. And finally, we have to capitalize on this here relation. We're told that the rate with which the magnitude, the radius vector of the moving point M changes, it is proportional to the distance of that point from the origin. In other words, in some sense, intuitively speaking, with the physicist hat on, the point M moves the faster the further away it gets from the origin. And conversely, if we were to reverse the flow of time and see the point M, or in some sense play back the movie that we capture of the point M moving in the traditional forward flow of time, we will see that as the point M gets closer and closer to the point O, it slows down more, it slows down. So how do we translate this into the language of mathematics? Well, that's quite simple. Look at this. We simply write that the rate with which the length of the radius vector changes, dr over dt, is equal to m times r. This is it. This is how straightforward it is. And you already know what we do. We separate the variables. From here it follows that dr over r is equal to m dt. Remember, m is a constant, by the way. What is the unit of measurement of this constant real number, or the coefficient of proportionality? Well, if the velocity or the speed is measured in the units time, distance over time, this is the velocity. And then what is the magnitude, what is the unit of measurement of m? Well, it follows that m is measured in units 1 over time, because we have distance over time. So 1 divided by, let's say, a second. This is the unit of measurement of our proportionality constant m, and this is it. So we take our equation dr over r is equal to m dt. We integrate both sides of this equation from initial radial displacement of the point M from the origin r0. Think about it, why we cannot really cannot integrate from 0, then to the current one, and then times wise from 0 to t. Now these integrals are more than straightforward. From here it follows that we have logarithm in base e of r minus logarithm of in base e of r0 initial distance of the point M from the origin is equal to m times t. According to the basic property of logarithms, this becomes the logarithm of the ratio r divided by r0 is equal to mt. From here it follows that r divided by r0 equals to e raised to the power mt, and from here it follows that r is equal to r0 times e raised to the power mt. So now we have our third equation. Let's write it down over here officially. R of t is equal to r0 times e raised to the power mt, and this constitutes the law of motion of our point in the polar coordinate system in space, the spatial polar coordinate system, and the transition from the polar coordinate system in space into the traditional x or y z Cartesian coordinate system is more than straightforward. That is, in this case, all we have to do is realize that the orthogonal projection of the point M onto the underlying plane x, o, y results in what? Results in the projection of the radius vector OM onto that plane, and the length of the line segment OMXY is given by what? Well, we either multiply this radius vector, the length of the radius vector OM, by the cosine of psi 0, cosine of psi 0, but because of this relation, it is equivalent to multiplying the length of the line segment OM by what? By the sine, trigonometric function of sine evaluated at the angle lambda 0. So let us write down this relation together for one coordinate. For example, what will be the coordinate x as a function of t? Well, it will be the length of the radius vector OM times r of t times the, in this case, it will be sine as a trigonometric function of sine of lambda 0 times what? Look at this. For the x coordinate, we also need to multiply the length of the line segment OMXY, which is this magnitude right here, times what? The traditional, if you look down onto this coordinate system, this will be our favorite x or y coordinate system. And here, the point, let's say MXY rotates counterclockwise about the origin. So what is the value of the coordinate x? Times the cosine of the dihedral angle phi, or the longitude of the point, times the cosine of phi. And this is it. Now we borrow the expression for the length of the radius vector r as a function of t, or from here, from the polar coordinate system that we constructed in space. Now what can we write down? Well, let's write it down right away. And now that you understand how we obtain this expression, we will also steal the function phi of t from here. It's omega 0 times t. So you now understand the way we do it is as follows. It will be the initial position, initial radial displacement of the point M, r0 times the value of the trigonometric function of sine evaluated at the constant angle lambda 0. It is one and the same angle. This is one and the same angle. Times, this time what? The cosine of omega 0 t times e raised to the power mt. And again, one more time, several episodes ago, we dedicated a good amount of time. We evaluated the corresponding integral in 3 creative ways. You see how naturally in physics these integrals emerge. Trigonometric function, exponential function, trigonometric or exponometric, if you will, exponential and trigonometric. Same thing, what will happen for the y component of t? Well, we see that the y component of t is shown over here. Look at this. It will be this line segment, OY, shown in blue, this piece. And what is this? Well, this is the projection of the point mxy onto the y-axis. So we take the line segment OMXY and project it onto the axis OY, and that means what? We multiply it by the sine of the dihedral angle phi, or the longitude of our point M. So here we will have right away R0 times, again, the trigonometric function of sine evaluated at the angle lambda 0 times sine of omega 0 t times e raised to the power mt. Again, it should be evident how we constructed this equation, and the last equation is for the z component. And what is this? Look at this. This is directly our radius vector OM projected onto the axis z with what? This time the trigonometric function of cosine of the angle lambda 0. Plus, of course, we don't forget about the fact that the radius vector varies over time. So here the expression will be the following: R0 times the cosine of lambda 0 times e raised to the power mt. And these three equations represent the law of motion of our point M over the outer surface of a right circular cone in the embedded traditional Cartesian x, y, z coordinate system. And you should have no problems with constructing a slightly different parameterization of the law of motion of our point of the outer surface of a right circular cone if in this expression over here, which we established based on the problem statement, we exclude the time variable t. This will be the dihedral angle phi divided by omega 0, the longitude of our point in the three-space polar coordinate system. And if we uniformly replace this time parameter t everywhere else in these three expressions, basically we will have to replace t over here and over here. This becomes phi, this becomes phi, and this becomes what? This becomes m divided by omega 0. We fold this in yet to another constant real number, and we have the following three laws of motion over here shown on the bottom right of your screen. And again, this is just a different way to parameterize the motion of the point M over the surface of a right circular cone. Here we have, again, don't forget that we have these functions x, y, and z have a parameter of the angle phi, the longitude of the point, and it shows up twice, here and here, in the trigonometric function of sine and the exponent, but here it shows up only once as the exponent of the base of the natural logarithm e. Officially, the trajectory that the point M traces over the surface of a right circular cone is called a conical spiral. And now that we have its various representations or various laws of motion as a function of time, as the function of the dihedral angle, to which we refer as the longitude of a point M in the spatial polar coordinate system, we can ask the following question: what will happen if we cut the trajectory of our point at any time with a plane that is orthogonal to the z-axis? Or in some sense, what will happen if we take the trajectory of our point M and project it on the base of the corresponding right circular cone, for example, on this plane shown over here, this plane, or in some sense, if we compress it and drop it onto the x or y plane in the traditional form. And the way we do it is by completely omitting or forgetting about the motion that happens, that unfolds along the z-axis, and only consider the equations of motion of our point in the x or y plane as x coordinate and y coordinate. And that is why, and that is where the romantic mechanical model of this problem that I came up for you at the beginning of this episode should actually be quite helpful, because if we forget about the motion of the point M along the z-axis, and that's actually another exercise I wanted to mention for you. Once you decompose the motion of a potentially very complex or complicated motion of a point into its independent motions, then you should be able not only to trace in your mind's eye the individual independent motions, but you should be able to combine them in an arbitrary fashion. For example, let's say we forget about the rotational motion of the point and only combine the motion of the point M along the z-axis and perpendicular to it. What will happen? Well, then evidently that point will move strictly in a straight line that is inclined by the specific angle, which is determined by what? By the ratio of the lengths of the corresponding line segments, as I explained. The vertical telescoping arm, the orthogonal, the horizontal telescoping arm, and so on. Or let's say we forget about, in our case, about the motion of the point M along the z-axis and only consider the motion in the proverbial x or y plane. What will happen then? Well, then our point mxy is moving along the rotating straight line OP in such a way that, think about it. So here, if we consider only these two equations, then once we square them both, as shown over here, and take the square root of it, look at this. This is a constant term, factor it out. This is one and the same exponent, take it out. And here we have the sum of squares of what? Cosine square plus sine square, the positive unity. So this is what we have in the end. R0 times sine of lambda 0. This is a constant real number, which represents the initial position of the point mxy in the x or y plane, times the exponent times e raised to the power k times phi. And what is this? Well, this is actually a logarithmic spiral. So we solved this problem in season 3, episode 22, while we were working on the solution of the physics problem S3E35, and over there we came up with this equation over here. Here we have to put the index 0 also, and remember that in the problem, in the physics problem S3E35, we actually also arrived evidently and of course at the equation that is the equation of a logarithmic spiral, but from a different perspective, from a perspective of a physicist, where we stated that the sample point is executing a motion in the plane in such a way that its tangential acceleration captured with the lowercase a and its normal acceleration captured with the constant b, with the symbol b, are constant non-zero numbers. In other words, a is a constant non-zero real number, b is a constant non-zero real number, and a represents the tangential acceleration of the point, b represents the normal acceleration of the point. So under these conditions, there is no choice, no negotiations. This point executes precisely a flat or planar two-space motion in the shape of what trajectory? Logarithmic spiral. The same exact thing happens over here. We have a logarithmic spiral. This is the equation of the logarithmic spiral, which, one more time, we obtain by only considering the coordinates x and y in the absence of the change that unfolds over the z-axis. And for curious travelers, I would like to give you one more way to obtain the logarithmic spiral that by now we understand actually has many faces. This short segment is for curious travelers only, for those ones who want to see that the logarithmic spiral has actually many faces and can be, if you will, defined in many different ways. Here we start with this differential equation shown over here in the center of your screen. dy over dx is equal to x plus y divided by x minus y. Quite elegant, crisp, and beautiful, strangely symmetrical differential equation, because why not? Once we unfold this equation into this string of differentials, this is cross multiplication, nothing very interesting over here. This is, in some sense, middle school arithmetic, but non-middle school arithmetic here is the following. In the theory of ordinary differential equations, there is a notion of integrating factor, which is used in order to manufacture a complete differential from the material present in the equation. And here it turns out that I'll skip the gory details of the theory of how this integrating coefficient can be manufactured. Sometimes the manufacturing of the integrating coefficient is actually quite as difficult, if maybe not more difficult, than integrating the equation itself. So here, to cut the long story short, it can be shown as a separate exercise that the integrating factor is 1 over x squared plus y squared. In other words, if we multiply this equation through by the integrating factor, we have two fractions over here, or the ratios, if you will. And here again, we manufacture a complete differential on the left by moving everything under the differential. It's 1/2 of the complete differential of x squared plus y squared. This is how we, in some sense, it is somewhat transparent of where did this come from, this integrating factor. Here, the integrating factor is slightly more involved, but not much more involved. It's actually the ratio of two functions, so y and x. So here we represent it as 1 plus y over x squared. Once you bring out the x squared, multiply and do the right thing, you will see that this is exactly what happens. So here we come to here, and once that is done, we have, what is this? This is the complete differential, yet another way we fold it the second time. D something over something. This is 1/2 of d logarithm base e of our sum of squares plus d of the arctangent of y over x. And once we integrate this, another constant pops out. We write it down as log of c, like so. It doesn't really matter. And once we potentialize both sides of the equation, we have logarithm of square root is equal to minus arctan plus log c, another constant. And once we raise everything to the power e, and we have what? The square root of x squared plus y squared is equal constant c times e raised to the power minus arctan of y of x. And what is this? Well, this is the equation in the Cartesian coordinate system. But once we move from the Cartesian coordinate system into the polar coordinate system, polar flat or polar two space, this is what we have. Rho is equal to c times e raised to the power minus phi, and this is again a logarithmic spiral, shows up one more time in yet another way in which that beautiful curve can be defined. And now for the fun part. Now that we know the expressions for the x, y, and z components of the moving point m as a function, as functions of time, we take their first derivatives in order to compute the x, y, and z components of the velocity of that point. And again, I wrote down the expression for the corresponding derivatives and velocities here, here, and here. This is a trivial task, computing the first derivative. We know how to compute derivatives. The intellectual voltage in this work is actually hovering right above zero, right about zero. And now that we know the components, we know the velocity as a function of time. This is a square root of the squares of its x, y, and z components. Once you do the math, you will fold this into the following expression. Why is that? Once you start squaring these guys, you will see that here there will be twice the product of these two terms will be minus with a sign minus, sine and cosine. And here it will be twice the product of these two terms, but this time with the plus sign, you see? So these guys will cancel out. You will have cosine square, sine square, favorable folding or convergence into the positive unity. And once you do the arithmetic, this is the expression that you will have for the velocity of the point m as it traces its wonderful path over the conical spiral over the surface of a right circular cone. And that means right away, once we know the complete velocity, we also know the complete acceleration as the first derivative velocity. Now, don't forget that this is a complete acceleration, and this will be comprised of two components. Again, a normal component and the tangential component, which I did not compute, but if you know these expressions, then with more work it can be done. The interesting thing over here I want to direct your attention to is over here, the direction cosine between the velocity vector and the unit vector on the z-axis over here, this guy. We know how to compute the ratio between the z component of the velocity and related to the magnitude of the velocity itself. Once you take this and divide it by this, you will see that the exponent will cancel each other out. And what does that mean? Well, that means that I usually like to designate the constant magnitudes with the zero subindex, meaning that these quantities do not change over time. Omega 0, lambda 0, in some sense m0 should be also designated like that, but for now we understand that m is a constant, everything is a constant, and overall, boom, we have our constant. And what does that mean? That means that we come across a phenomenon that we came across already before while we were solving the following problems. In season 3, episode 26, while solving the physics problem S3P6, we saw that we recovered the trajectory of the point as a right cylindrical spiral shown in blue over here, and every generatrix of this right circular cylinder is a straight line that runs like this, parallel to its axis of symmetry. And the thing is that with the right cylindrical spiral, that spiral intersects all the meridians at one and the same angle. We proved that in this episode while solving this problem. Not so long ago, in the loxodrome episode, season 3, episode 30, while we were solving the problem S3P7, the physics problem S3P7, there we postulated right away we want to see the motion of a point in such a way that it cuts every meridian, but this time on the sphere. The meridian on the sphere is what? Is an arc of a great circle, which results when the generating sphere is cut with a plane that passes through its center. So our trajectory, we demanded that it intersects every meridian on the one and the same angle. Angle, same, on the surface of the sphere. This is called a loxodrome. Again, this time the meridian looks like an arc of a great circle. Here the meridian is a straight line. Now come back over here, look at this. We proved again that as our point M traces its spiral, let's see if I can somehow portray it. It will be like this. Somehow it will be quite unwinding spiral like this. It will go like this. Here it will be like this. And you can see evidently that, judging by the expressions over here, look at this. We saw the expression with the angle phi, the longitude of the point, and because the exponent raised to the positive power never reaches 0, it is evident that as our point in reverse order, in the reverse time flow, spirals towards the origin, it executes infinitely many rotations or spins around the point, but never actually reaches it, or spends an eternity trying to get to the origin. So here, as our point M traces this conical spiral, it does it in such a way that it intersects every generatrix of this cone, or every meridian. So this will be the meridian, another meridian, another meridian. So every time our point will intersect such a meridian at one and the same angle at any time. So here I try to portray the following idea. Look at this. We crawl down the right circular cone, we step under and we look on the plane X or Y. From under, we get under the plane, and from under the plane, we look up at the right circular cylinder. And this is what we see. This is our origin, point O. This is our plane. This is this top plane right here. Say we cut it off here at this point. And now we draw these meridians. These are the straight lines that all converge at the origin. So the conical spiral that the point M traces will look as follows. Look at this. It will wind its way like so over the surface of a right circular cone. And again, due to this relation over here, we just proved with mathematical precision, if you will, that this trajectory has the same interesting property, that it intersects all the meridians of the parent right circular cone at one and the same angle. Now, this is it for the physics problem S3P8. I think in the previous segment I made a mistake and named that problem S3P9, but I apologize for that. This was the physics problem S3P8. And for our next challenge, we will take on the problem in computer science S3CS 8. If you have any questions about the physics problem, use the comment section under that episode, and I will take it from there. And the objective of the computer science problem S3CS8 is to construct an algorithm for detecting whether a linked list has a cycle or not. In other words, on the input into our algorithm, there will be a linked list, and that algorithm in a finite number of steps supposed to hold with a Boolean value, let's say 0 or 1, true or false, yes or no, however you decide to interpret this. And the meaning of that Boolean value is the following: yes, this linked list has a cycle, or no, this linked list has no cycle. So a traditional linked list where all the citizens are good linked list citizens, they all point to the next, and every pointer to the next element is unique. In other words, every element that points to the next contains the unique address. But it may so happen that through a not so careful but still careful enough manipulation of the linked list, it is broken artistically and cleverly in such a way that some pieces of it remain lost in memory. This is a memory leak, but one of the nodes in the linked list points to a previous node. In other words, here, this, for example, node points to this address, and this node points to this address. So these two addresses are one and the same, or a duplicate address. Write or construct an algorithm that will detect such a cycle in the linked list, or it will say there is no such cycle in that linked list. Now, this is it for this episode. Thank you very much for your time. Thank you for watching. I will see you in the next episode, in which I will present my solution of the computer science problem S3CS8.